Yes.
Okay. So, assignment 7, again, will be due Tuesday, 27th, and at 5 p.m. or by 5 p.m. And then final exam will cover chapters 6 and 7 on Wednesday, 12:30 to 2:30. Meet and collaborate also as usual. So I'm trying to get the assignment 6 graded. Hopefully get that back to you tomorrow. Again, get started if you haven't already on assignment 7. So, send me initial drafts of solutions by email, PDF format, please. And I can comment on those for you. And as far as questions for the final exam, again, stuff like stuff that's similar to homework problems and examples done in class. Okay? And that's that. So, are there any questions on assignment 7? What about number 1? What needs to be done in number 1? What do you need to do? What needs to be done in number 1 to show that m cross n is a metric space with that distance function shown there? What does 1 actually have to do? You have to show that the distance function does what? You have to show that the distance function satisfies
the properties.
the 4 properties. And you do that by breaking the distance function for m cross n, right, down to its constituent parts using the distance function for m and the distance function for n. Right, the distance function for m cross n is defined in terms of what's the sum of the distance function in m plus the distance function in n, and those functions, by assumption, satisfy properties 1, 2, 3, 4. Right, 1, 2, 3, 4, and m and n. M is a metric space with distance function dm, and n is a metric space with distance function dn. So the fact that this d satisfies property 1, 2, 3, 4 comes from the fact that dm and dn satisfy properties 1, 2, 3, 4. So you just have to run through those 4 properties and break it down into its constituent parts, just like how we did in with relations and partially ordered sets. We've done things like this a few times already, trying to get you used to the notion of Cartesian products. And then 2, use techniques very much the same as what we did in the example about disjoint open balls around different points. So why don't we call that? Why don't we call this example 1? All right, so Smash that phone. So for number one, show, so assuming dm and dn satisfy properties 1, 2, 3, 4, show that D satisfies properties 1, 2, 3, 4 by breaking down D into terms for dm and dn. Some similar ideas to what we've been, doing with Cartesian products all along. Again, please, guys, get started on this and send me some drafts. I will tell you, I will write comments. I'll tell you if it's right or wrong. And if it's wrong, I'll tell you why. Before you actually hand it in. I mean, you get that back and forth, discussion between you and I. And that's how, really good learning happens. Really good, if you're not getting it by yourself just right off the bat, then that give and take, that conversation is what's going to help you. One person with assignment 6, he sent me, he back and forth like 3-4 times and 2-3 times, something like that. And then the last time it was just correct. I'm like, okay, this is fine. You don't even need to hand it in. You just get full credit. Number 2, so similar techniques to example 1. Okay, so, go over example 1, and try to understand that, and then number 2 shouldn't be an issue. All right, so let's get back to our discussion then on sequences, and, that'll be everything for the course. After we talked about open balls, so remember what the open ball was. Given a metric space M, and X in M, and a positive real number R, the open ball of radius R centered at X is BRX. That's the way you denote it. It's the set of all Y, such that the distance from X to Y is strictly less than R, by the way. Not less than or equal to, strictly less than R. That's the open ball. If you said less than or equal to, that's something called the closed ball, but we're not going to bother with that, okay? Just open ball is the important issue here. And, in R cross R, the various open balls, with the various 3 different metrics, you get 3 different definitions of open ball. Yes, they're not all shaped like balls, okay? But the Euclidean metric is sort of the intuitive standard. It is the intuitive standard. And then in example 1, given X and Y in a metric space, X and Y are unequal, there are open balls, BRX and BSY, that are disjoint. You can put disjoint open balls around 2 distinct points. How does that happen? Well, you just take the distance from X to Y, and that's a positive real number because that's property 2, right? Because they're not the same, so the distance is positive. Cut that distance in half and put the balls of radius d over 1/2 dxy around each point, or 1/3 dxy if you want to, if you want it to be kind of, more obviously disjoint. But 1/2 is good enough. Okay, so you can always do that in a metric space. No matter what the metric, no matter what the metric space, given any 2 points, there's always open balls, disjoint open balls around those 2 points. And we did, here's the proof right here. So that's definitely something you want to know. And then we defined sequence. Okay, so again, with metric spaces, all you can assume about metric spaces are properties 1, 2, 3, and 4. There's nothing else you can assume about metric spaces in the abstract. There is no algebraic structure. You can't add things. You can't compare things. Right? You can't say like x and y, like x is less than y. You can't say that. There's no ordering on elements in the metric space. You can't add them. You can't look at x plus y in an abstract metric space. I mean, given a particular metric space, the real numbers, yeah, you can add things in the real numbers. Okay, but we're not dealing with that. We're just dealing with the distance function. Well, what can you do just with the distance function that you normally do with the real numbers? Well, we can talk about convergence. Very important concept in the real variables class, 4310, 4320. Right? Obviously, it's really important because calculus is all based upon limits and conversions. So you start with this notion of a sequence. A sequence in a metric space, just some list of elements in the metric space. x1, x2, x3, x4, x5, x6. You think of it as a function from the natural numbers to the metric space itself. Right? So x1, you can think of it f1, f2, f3. It's a function from the natural numbers to the metric space. Although you don't use that functional notation, you use this kind of notation. Now, normally you write xn to denote the sequence in its entirety. So xn is equal to this whole thing. But you also use xn to denote the nth element of the sequence. And it's clear from context which is which. Right? If you said that xn is minus 1 to the n, you mean this sequence here. If you said xn is 1 over n, you mean this sequence here in the real numbers. Right? Not that your metric space is the real numbers. All right. Convergence. So here's the big idea. We say that we write xn arrow L to mean, not xn implies L. I know it's the same notation as implication in propositional logic, and that's just that's just part and parcel of mathematics, is that the same notation is used for different things. Although real variables and propositional logic don't really overlap, so there shouldn't be too much. There shouldn't be any confusion. So xn arrow L means xn converges to limit L. The definition of xn converges to L, okay, when for every positive real number, so you think of R as something tiny, some tiny real number, 0.0000000001, something like that. For every tiny real number, positive real number, there is a natural number n, such that the sequence gets stuck in that tiny ball around the limit. At some point, down the line, doesn't matter how far down, the sequence, ends xn, xn plus 1, xn plus 2, xn plus 3, capital N plus 1, 2, 3, so on and so forth. All that's in the ball around the limit. Right? So here's the ball around the limit. And the sequence, it's bouncing around. Maybe it goes in the ball, maybe it comes out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, comes back out. 13, 14, come back out. 15, whatever. But at some point, x1 million, it gets stuck in here. x1 million, x1 million and 1, x1 million and 2. No matter how tiny that ball is, okay, the sequence gets stuck in that ball at some point. Another way to say it is this. So this is a statement for all there exists. For every tiny real number, there is a natural number such that when m exceeds the natural number, the distance of the sequence to the limit is less than r. So that sequence gets as close to the limit as you'd like it to. So using that definition, okay, now the sequence 1 over n in the, in the metric space of just real numbers. Okay, I mean, it's no, it's no big deal to say that 1 over n converges to 0. We all understand that intuitively, right? It needs no proof. It doesn't need a proof. But, we have the definition. Let's give the proof according to the definition. Okay, so how do you prove a sequence converges? You let r be bigger than 0. So r is a tiny real number. How tiny? Really tiny. Okay, but you don't say, well, you don't know what it is. So you just call it r. And just think of it as something really small. Okay, pick any natural number n that exceeds 1 over r. Right, since r is really small, right, 10 to the negative 20, right, 7 to 10 quadrillion, or whatever that is, or not quadrillion, septillion or something, whatever that is, right, pick a natural number that's bigger than that. Right, so now, whenever m exceeds that natural number, capital N, the distance of 1 over m to that alleged limit, 0, is equal to, well, in this metric space, that's the definition of the distance function, and that's just 1 over m, which is less than or equal to 1 over n, because m exceeds n, and 1 over n is less than r, as we said up here. And we did this example here. So in problem number 1 on assignment 7, you prove the following. If m is a metric space with distance function dm and n is a metric space with distance function dn, then m cross n is a metric space with distance function d, defined this way. Right? Just like we had on that assignment there. All right, let's prove that the following is true. So we're just going to assume that, let's assume that's true, because you're going to prove it. Okay, so now, let's say that xn is a sequence converging to L in metric space M, and yn converges to limit k in metric space N. Okay, let's show that the sequence xn yn converges to L comma k in M cross n. The trick in here is something that you'll see in 4310 a lot. Okay? So how do we prove a sequence converges? Okay, well, let r be bigger than 0. So r, we need to start with, any r bigger than 0. So pick one. Okay, let r be bigger than 0. You don't know what it is. Okay, but it's something really small. All right, because xn converges to L, this is the assumption in M. Because xn, there is by definition, so by definition of convergence, there is a natural number, R1, capital R1, such that for every m exceeding capital R1, the distance from xm to the limit is less than r over 2. Why not r? Well, we want to show that this sequence in m cross n converges to this limit, L comma k. And we're going to do that, we're going to show it satisfies the definition of convergence for r. Okay, but in order to do that, we need to use the definition of convergence in some way that gets us to what we're looking for. Okay, so since r is bigger than 0, well, half of r is bigger than 0 as well. So by the definition of convergence, the sequence xn eventually gets stuck in the ball around L of radius r over 2. Right, so there is a natural number r1 such that for every m bigger than r1, the distance of xm to L Similarly, because yn converges to k in n, this would be distance m, excuse me. Because yn converges to k in n, there is natural number r2, such that for every m exceeding r2, the distance in n from ym to the alleged limit k is less, not the alleged limit, the actual limit k is less than r over 2 again. Now, why does that work? Why does that help? Take a natural number r, whichever one of r1 and r2 is bigger, or if the same, let r be the same. Why? Why do we do that? Why do we let r be the larger of r1 and r2? Well, because now if m exceeds this natural number, capital R, then m exceeds both r1 and r2. Right? R is just the larger of the two. So anytime you exceed capital R, you exceed both r1 and r2 at the same time. So since you exceed both r1 and r2, we now get the following. The distance of xm, ym, that pair in the Cartesian product m cross n, to the point LK is, by the definition of the metric d, the distance in m from xm to L, and the distance in n from ym to k. Well, this one is less than r over 2. That one's less than r over 2. So these are both less than r over the together, their sum is less than the sum r over 2 plus r over 2, which is just r. So for every r bigger than 0, there is for every little number, positive real number, little r bigger than 0, there is a natural number, capital R, such that when m exceeds capital R, the distance of xm to ym to lk is less than r. That's what we want. Again, go over these examples. Okay, exam problems similar to the homework and examples done in class. Similar to the homework and, pretty much the same examples done in class. And nothing else. So since we're squeezed a little bit here, I will tell you, please look at these examples and understand them. All right. One more example of usage of sequences. Or maybe we'll do two. But before that, we need a definition. Let M be a metric space with distance function D. Okay, a subset O is called open when for every x in O there is r bigger than 0 such that the ball of radius r around x is contained in O. So here is the intuitive picture. And so here's your set O, and then here's some x inside that set, and there is some ball around x that stays in O. There is some ball around x such that stays in O. So that is an open set. So here's a non-example. So let So in the space of real numbers, consider the closed interval (0 to 1). Right, that's equal to the set of all x such that 0 is less than or equal to x less than or equal to 1. This is not open. This is not open. Why? So here's the metric space of real numbers. Metric space of real numbers, think of it as you know, an infinite ruler. All right, so here's the 0. Oops. Here's the 0, and here's the 1. Okay, which number in X, which element in X, do you think I can't put an open bool around it and stay in the interval? Where does this open ball thing fail? Well, there's sort of the obvious choice.
Zero and one.
Yeah, 0 or 1. Either one is fine. All right, consider x equal to 1. Well, so let r be any real number. Let r be bigger than 0, and consider the ball of radius r around 1. Well, that's equal to what? Now let's do it around 0, actually. The ball of radius r around 0. It's everything whose distance from 0 is less than r. Everything whose distance from 0 is less than r. What's that going to be exactly? In the space of real numbers, where distance is the same thing you've been working with all these years. What's the interval of interval? What's the ball of radius r around 0? Which real numbers have distance less than r from 0?
None.
None. Suppose r is equal to a half or something like that. Give me a real number whose distance from 0 is less than a half.
A fourth.
A fourth. Or 0 itself, right? 0 itself. The distance from 0 to 0 is 0. There's always something there, right? So what is it going to be in general here? Which numbers around 0 have distance less than r? The set of all x such that what?
X is less than one.
Less than, not 1, but
R.
less than r. Set of, well, so actually absolute value, well, let's say set of all x such that minus r is less than x is less than r. Right? So the ball, it's actually the open interval, right? From minus r to r. This notation is really misleading here. Right? So here's minus r and here's r. Is that a subset of the interval from 0 to 1?
No.
No, absolutely not. This is not a subset. So certainly BR0 is not a subset of the interval from 0 to 1 for any r bigger than 0, no matter how small. Right, so that's not an open set. Hence the reason it's called closed in in a calculus type setting, or when you're just talking about the real numbers on its own, like you did in calculus. Here is an example for any metric space, right? When we were defining balls, we described them as how? Balls were described how? When we defined the thing. Right, this thing is called what?
Ball of radius R centered around X.
Yeah, the open ball, we call
Ball
it.
with a radius centered around a point.
Yeah, right, the open ball. So, that suggests that this is an open set, which, it always is. But let's give it a proof. This is also a nice discussion of technique for problem number 2. Okay, so let M be any metric space. X be an element of M, and R be any real number bigger than 0. So let's show that the open ball of radius R around X is an open. Actually, why don't we call it V? Is an open set. So the open ball is indeed an open set in any metric space. Right? Let's take a look at the definition of open set again. Let's absorb that definition. For any, so a set O is called open when for every X in the set, there is an open ball around X that stays in the set. There is an open ball that stays in the set. And this example we did here, this non-example, here the closed interval from 0 to 1 contains the number 0 in the space of real numbers, and no open ball around 0 stays in the interval from 0 to 1. Right? So now we want to show that, for in this open ball, that any X that you pick in the open ball has an open ball around it, making the open ball itself an open set. Okay. So proof. So what we need to do is the following. Let X be an element of the open ball of radius R around V. Let's draw a picture to help us along here. The picture, well, in this sort of context, isn't a proof. Okay, but it helps illustrate the proof. So here's V, all right, and the ball has radius R. So now here's X right there. So we need to find a ball around X that stays in the ball of radius R around V. So what do we have to do? We have to define the radius of the ball around X and then show that it stays inside the open ball of radius R around V. Well, what radius shall we choose, do you think? There's only one number that we know. Well, there's two numbers that we know about here in this problem. Only two numbers. Well, there's R. R is a given number. And there's one other number that's kind of floating around in here.
R over 2.
Well, not having to do with R. Yes, of course, right. But not having to do with R. There's another quantity here that we can work with. Right, we have element X in the ball around V. So we also have the quantity what quantity that has to do with u and v. U and v themselves are not quantities. Right? This is just an abstract metric space. U and v aren't necessarily numbers. But there is a quantity depending on u and v that we do have. And that is what? Only 4 properties in a metric space. They all have to do with what? There's only 4 properties in a metric space, and they all deal with what?
Distance.
Distance, yeah. So since I have element x and I have element v, I've also got what?
The distance between the two.
Distance from x to v. So why don't we add that in here in our little picture? So picture says 1,000 words here. Okay, the picture is not the proof, but it for sure illustrates what we're getting at. All right. So what radius might we use here to get the ball around x not to go outside the ball around v? This is the distance from x to v. So we'll call that the radius around x. We're going to call it t. Let t be equal to what? What can we define this radius to be that will not go outside the ball around v?
1/2 dxv.
Maybe not small enough, right? I mean, the x could be like really close to the boundary here, right?
R minus dxv.
Perfect. Yeah. Let t equal r minus the distance from x to v. Okay? So let t be r minus the distance from x to v. Okay, what do we need to show? Let us show that what? So what do we need to show? I mean, you're right. That's the right thing to pick. But what must be verified? Your intuition is right that this distance t here, this distance t, it should be r minus the distance from x to v. And when you define it that way, the ball of radius t around x will not go outside the ball around v. But what do you have to prove? Your intuition has served you right, but intuition itself is not a proof. One actually has to prove that the intuition is correct. So let us show that what needs to be true.
That t plus dxv is less than r.
Let's look at the definition. You're on the right track, but let's look at the definition. All right, so O is open when for every x in O there is an r around there. So there is a real number r such the ball of radius r around x is still in O. We need to show this. Right? We
So prove
yeah.
d
Ball. Which ball? Ball of radius
x
X is in the metric space, but the ball of radius what around X? This number
T.
T. Ball of radius T is contained in our alleged open set, which is
Ball of radius R around V.
good, right? Okay, so how do we show that? I was really, on like the last assignment on the last exam, I was really a little surprised that we forgot how to show that, A is a subset of B. How does one show that A is a subset of B?
Both conditions are true. Or subsets of each other.
Yeah, how do you show that A is a subset of B? I mean, because on the exam we had to do that. Like we had to show that this set was a subset.
We assume that X is an element of A,
And
and then
that
show
never
that
yes,
element
that never changes. That's always the case. We want to show that this thing is a subset of this thing. I don't care what the things are. One has to start by taking an element here and showing it's an element there. That's always the case. Unless you got some other clever way of doing it, which could happen, but under normal circumstances, pretty much it always goes like this. Okay, so to do so, so we've already been using X and Y here. Let's go to something different. Let P be an element of the ball of radius T around X. We need to show that P is an element of the ball of radius R around V. How does one show that P is in the ball of radius R around V? What governs the ball of radius R around V? I guess we could use Y. Let's use Y. What makes something in the ball of radius R around V? There's only one property that defines that, which is that the distance from Y to V is less than R. Okay, the distance from Y to V. Well, by the triangle inequality, that's property 4, right? By the triangle inequality, the distance from Y to V is less than or equal to, why does it always do that and not go away? It's less than or equal to the distance from Y to X plus the distance from X to V. Well, the distance from Y to X is what? By definition. Well, because
R over 2.
Y is an element of, what was it, the ball of radius T. The ball of radius T around X. Because Y is an element of the ball of radius T around X, this is what? Less than
T divided by 2.
Oh, just T. Just T, right? The ball of radius T around X is everything that's distance less than T from X. So that's T, right, plus the distance from X to V, right, which is equal to, right, definition of T, right, T was equal to what? R minus dxv, right? So this is R minus dxv plus dxv. Get it all on one line. So this is equal to, so T was equal to R minus dxv plus dxv, which is just R. So there it is. So the distance from Y to V is less than R. The distance from Y to V is less than R, right? We're working with a string of inequalities that all point in the same direction. Equalities and inequalities that all point the same way, in this case to the left, right? So you get that the first is strictly less than the last, right? Or if you had equality at some spot, you'd have to have not less than, but less than or equal to, but well, here we're good. So, which makes y an element of the ball of radius r around v as required. Right? We must show that that's the case. And that's it. So triangle inequality gets a lot of play. You know, I mean, it gets a lot of screen time. Right. So we show that this B is an open set. Right. We took an element of the ball B, and we defined a radius T around X, and showed that the ball of radius T around X stays in B. You know, we had to be careful about, exactly what we mean by B and exactly what we mean by radius, but we did it. Right? We let X be in the ball of radius R around V. T is equal to R minus the distance from X to V. It's actually the only two numbers we know about in the setup here. And now let's show that the ball of radius T around X is contained in the ball of radius R around V. And that's what we did. All right, one final example here. Let O be an open set in metric space M, having distance function D. Okay, let Xn converge to L in metric space N. So Xn is a sequence converging to L in metric space N. And assume that Xn is not in the open set for every N. So we got an open set in the metric space, and we got a sequence outside that open set. And the sequence converges to L. What has to happen is that L is not in the open set. Prove that L is not in the open set either. So proof is by way of contradiction. So by way of contradiction, assume that L is an element of O. By the definition of open set, what has to happen? Because L is an O, and O is an open set, what?
L is a subset of O.
L is an element of O. Right, you got your open set O. You've got this element L inside of O. Right? By definition, what has to happen? There is a subset having to do with L inside O, which is what?
X sub n.
It's an open set. What was the definition of open set? A set is open when for every X in O, there is what around X?
R greater than 0.
Such that
B sub R, X is equal to 0.
right.
Or
And it is a subset of O. In this case, we're talking about L, not just X, but what's this? So there is a ball of radius r around L that stays in the open set. Now remember, xn converges to L. Because xn converges to L, right, what has to happen? There is some natural number n such that what? The sequence gets
Stuck in the ball.
stuck in the ball. But the sequence is where in regard to the open set?
The open bar ball around L.
It's the sequence is not in the open set, period. Right? So because xn, there is some n and then the natural numbers such that x capital N, x capital N plus 1, x capital N plus 2, blah, 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 are all in the ball of radius r around L, which is a subset of O. Right? But by assumption, that xn is not in O for all n. Right, so we're talking about a sequence, right? Like x1, x2. Maybe I should do this in blue or something. x1, x2, x3, x4, blah, blah. Stop. Don't tell me it's going to crash on me. Okay. Let me close this real quick. x4, x5. The sequence stays outside the open set. It never goes in that open set at all. That's what we assumed. So we assumed xn converges to L, and we assumed that the sequence xn is not in the open set. So it never goes in the open set. In particular, it's not going around that ball around L. That's the contradiction. Right? By the definition of convergence, because xn converges to L, at some point the sequence gets stuck in that little ball around L. But we assume that xn is not in the open set at all. That's the contradiction. A contradiction. Therefore, L is not in O. Right. We assume by way of contradiction that L was in O, and that, that led us to the contradiction that the sequence, in order to converge to L, has to actually go inside the open set, but it can't. Okay. So that's all the material. All right. For the final exam, okay, these examples that we've done, I'm going to ask like the exact same thing for 1 or 2 problems at least on the exam. I mean, we're only going to do 4 problems. Okay, 2 from chapter 6, 2 from chapter 7. No second principle of induction. Don't worry about that, all right? No second, well, actually, hold on. If we're going to do induction, yeah. 2 problems on induction. Should we do the second principle? No, nah. Yeah, no. Two problems on induction. No second principle. Okay. No second principle of induction. And two things on metric spaces. Just from the examples we got here. Okay. I'm not going to pick anything other than what we've done as examples. So study these examples. Okay. And you can have your 8.5 by 11 one piece of paper. Handwritten, not the notes, of course. All right, handwritten notes for the exam. Okay. All right. So send me your drafts for the homework, and then I will. If you want to meet, we can meet as well. Send me an email, or email if you want to set up a time for us to meet on Collaborate Ultra. And otherwise, I'll see you on Wednesday. Okay. All right. Have a good day, everybody.